Why is signal-to-noise ratio critical for EEG BCIs? Imagine trying to listen to a whisper in a noisy room. That's similar to what brain-computer interfaces face when trying to pick up signals from the brain. In neurotechnology, especially with brain-computer interfaces, the clarity of the signals matters a lot. The signal-to-noise ratio is a way to measure how strong the brain signals are compared to background noise. The higher the ratio, the easier it is to tell what the brain is really saying. EEG or electroencephalography-based brain-computer interfaces record brain activity through sensors placed on the scalp. These sensors are non-invasive, which means they don't require surgery. But this also makes the signals weaker and more prone to interference. Noise can come from muscles moving, blinking eyes, or electrical devices nearby. This noise can drown out the actual brain signals, making it hard for the system to understand what the brain is trying to communicate. When the signal-to-noise ratio is high, the brain signals stand out clearly from the noise. This helps the brain-computer interface work more accurately. For example, if someone is using a brain-computer interface to control a wheelchair, high signal clarity means the system can respond correctly every time. If the ratio is low, the system might get confused and make mistakes, which can be frustrating or even dangerous. Many brain-computer interfaces use specific signals like the P300 wave, which happens about 300 milliseconds after a person recognizes something. Detecting this wave accurately depends on having a good signal-to-noise ratio. If noise levels are high, the P300 might be missed or misread, leading to errors. That's why researchers work hard to improve this ratio. They do this by placing electrodes carefully, reducing electrical interference, and using smarter signal processing techniques. Making these improvements means the system can better distinguish real brain signals from noise. This results in more reliable communication, especially for people who are relying on brain-computer interfaces for help with mobility or communication. In the end, a good signal-to-noise ratio is the key to making EEG-based brain-computer interfaces more effective and trustworthy. It's what turns faint brain signals into clear commands that machines can understand and act on.